I see our next speaker online. Hello, Dino. Great to see you on this conference.
Hi, can you hear me?
Do you hear us? Yes, we hear you well.
Beautiful, I'm here, ready to start.
Awesome, awesome, awesome. Yes, and Dino is not our first time guest in Cloud Builders. We already had his awesome session on one of the meetups, so I'm super excited to continue our collaboration. Dino is CTO at Creonet and software and solution architect, now active in machine learning, general AI, and smart cities. And I think his session will be awesome continuation of what Dmitry started to introduce during his demo. How can we apply all these cool things in data science and data engineering to make our solutions better, to make lives of people better? Dino, the stage is yours.
Thank you. So, this is not going to be a strictly technical session in the sense that I'm not going to show any kind of code. I'm not talking specifically about code that you can use or just read or get inspired by related to machine learning frameworks, but it's a more business oriented kind of talk that was inspired by having seen for quite a bit of time a number of job posts from companies of any size, just focusing on data scientists and transmitting the idea that all you need in a real world environment is knowledge of data science. And as I see things instead, for what has been so far my experience in the world, practical, realistic scenarios of machine learning is okay. Data science is good, is great, and we will talk about that. But it's also time, especially if you are managing a company or managing a team that is deeply involved in AI, whatever that means, projects, it's time you start thinking more about what runs around the core, the beating heart of artificial intelligence, and this is precisely what in this presentation I called data engineering. If I have to kind of summarize this presentation, I would play a sort of a joke connecting science and engineering and data science and data engineering. So the primary takeaway from the coming few minutes is, as much as in real life and even in history, science showed the way to go, proved that certain things could be achieved. It was then engineering and in recent years technology that made those things that science proved possible actually products we could buy and we could enjoy. So if we shift from science and general engineering to data science and data engineering, we are talking about software. We are right in the middle of the software space, and in this context, AI is nothing different from just plain software. Maybe more intelligent software than the software we are commonly used to write and even face as users. How many million times we complained as plain users of certain features that made the software too rigid, or the inability of the facing software to automatically recognize or realize a number of things. How many times we just dreamt of, oh, what if the software could tell me what is interesting in this particular business context. Okay, now machine learning makes it potentially possible. I mean, it's not free, it's all but free, but it's definitely possible, much more now than it was only a few years ago, makes it possible to achieve, to implement more intelligent features. But we are still talking about software. Now, this is a low resolution, okay, but it's not that the primary point, low resolution screenshot from a cartoon. As you can see, it shows the practical solution that the dog and the man found to bring a huge sandwich into the house. Now, outside the cartoon, it's so easy to realize that they could have found many million different ways, maybe rotating their position to get through the door with that huge sandwich without the need of breaking, enlarging the wall to make the sandwich pass. Now let's try to transpose this cartoon, funny screen to the world of data science, to the world of practical artificial intelligence. It's not much different from when, as a team of data science, you suggest or you actually build a 100-layer neural network that costs an incredible amount of money to train, and even enough money to run for the happiness of cloud providers, but you forgot to try a simple, maybe in linear regression algorithm before you jumped into the huge and even attractive project of trying to build a huge neural network. Now, what is the real lesson behind this apparently stupid or just funny screenshot from a cartoon? Why are you going to do some AI? Is it just that you want to jump on the AI bandwagon just to have something you can sell to your customers or you can market through your social channels as intelligent? Are you just trying to sell yourself or your company, your services as, oh, we do AI, we are strong with that, we have plenty of projects? Using concretely more intelligent, more powerful tools that come from the space of machine learning is primarily a matter of understanding and having clear in mind which problem, specific problem, are you trying to solve. If you don't know exactly, very well defined the problem, you are missing everything. I mean, it's so obvious to say that, oh, companies can take advantage of AI. This is true, but it's a tautology. It's obviously true. The point is, how do you make every single possible scenario to improve actually better through the concrete implementation and application of more powerful tools? So a neural network, just to switch back for a second to the previous cartoon frame, a neural network does its job. I mean, it's always a solution to any sort of problem that has to do with prediction and classification. But is it the neural network and the effort to build it and to test it, right? Was it just overkill? Was it appropriate? Is the result you're getting only achievable through the use of a neural network? Sure that a simpler approach, whether it's another shallow learning algorithm or just a basic decision tree or even a bunch of ifs, wouldn't this be maybe a simpler and nearly the same as effective solution for the problem, for the specific problem you have to solve? Let's talk about software now. So now, in terms of overall view, what we call machine learning is can be described in terms of two main areas: the area of thought, thinking, and the action. In the middle, there is something that is called generically the learning algorithm. And the learning algorithm gets the thinking side data in the form of a data set, typically a cube or a matrix of data, and produces out of the learning stage something that is nothing more than a computation graph. Of course, the complexity of the computation graph is varying to a large degree depending on the learning box that you have set up. So if the learning box contains one or more likely multiple connected pipelined neural networks of different types, because a neural network can be of many different types, the computation graph is fairly complex. If you have instead in the learning box a simpler shallow learning algorithm, the computation graph can be as simple as a decision tree automatically built, or like a polynomial whose coefficients are essentially learned during the learning process to stay as close as possible, but not on top of the training data that has been provided. Another view of this is, okay, on the pipeline, training data set, learning, computation graph, the outcome, data on top of that, software underneath that. Now, this view here, data on top and software at the bottom, this view, basic view, originates in the real world when we, as people working around or inside a company, try to implement this concretely, has brought to a sort of a dichotomy where there is a sort of gray area data that incorporates the pipeline of building a model that actually is the serialization of the computation graph and nothing more than that. And outside of this gray area, nearly distinct from that, we have software. And software means how to make use of this gray box. Most of the time, the role of software is reduced to that of just calling a distinct, separated web service. So the typical vision in business is a data science team that is entirely and totally responsible for getting the data, for shaping the data, for choosing the algorithm, for running the algorithm, for testing the quality of the results, and then to serialize and deploy to production the trained model that finally the software, whether it's Java, whether it's .NET, whether it's a mobile application, whatever it is, can just call via REST, via gRPC, or via whatever network-based kind of protocol. But at the end of the day, we observe in this common scenario a neat dichotomy. Data and science is on one side, and software as a plain client lives on the other edge of the space. Now, I don't believe that this is the most effective way to approach real-world development of machine learning solutions. And here is a different perspective, a different view of developing real world, actually effective, whether they are real world or not, just effective machine learning projects. Of course, there is an arrow that goes from left to right, starting with raw data, probably found in some sort of a data lake, okay, to the final application that makes use of the data through new functions delivered to the user. Along the way that moves from raw data, which are continuously, hopefully continuously generated by the business that run within a context, company context. On the way from there to the final application, I see three different roles operating. So it's not just data science and then the software application, but I see on the way from raw data to the final software application, there are three different roles that interact in some way, strictly connected and to some extent overlapping. It's the role of the data scientist, the role of the data engineer, and the role of the machine learning developer, software developer. Data scientist has a lot in the definition itself. Okay, data is the guy that knows about machine learning, that knows about algorithms, that knows about neural networks, the theory of those things, and the mathematical and statistical theory behind those things. The developer is a software developer, he's a software guy, but that knows a little bit more about machine learning. In between these two figures, these two operating roles, there is the data engineer that is essentially the missing link between those two elements, data science and just software, that everyone recognizes in machine learning scenarios. So there is a third role, the data engineer, responsible primarily for maintaining a structured and fresh the data as the data comes live continuously from just running the business. Let's get into some more details about the role, the intended role of data scientist and so forth. The data scientist, the role of a data scientist is essentially the role in which an individual has a strong mathematical and statistical skills and knows the techniques, the mathematical techniques from the sciences that deal more than other sciences with large quantities of data. And the primary responsibility of the data scientists is the ability to view through the data available and making reasonable guesses about what the data available can be turned to. I like to compare to, I like to associate the role of the data scientist to the artist. The ideal figure here is the sculptor that faces a beautiful block of marble and in some way views through it and kind of imagine the figure that it will produce through the sculpture art. A legend says that Michelangelo, once in full Renaissance era, faced a huge, wonderful cube of white marble from the Tuscany mountains, legend says that he saw through the cube of marble the figure of the David statue that he then created out of it, and that became a universal masterpiece of the sculpture art. So this is more or less the out of poetry, out of emphasis. This is essentially the role of the data scientist, making reasonable guesses, looking at the data and making reasonable guesses about what the data can have to offer. Now, to offer to whom? To the owner of the data, so the company. So the data scientist, whoever has a data science role within a company, has a key role to determine what the company can learn from the data he has and which artifacts or which final consumer products can be planned and for which business purpose. So in other words, an effective data scientist is not a figure completely avulsed from the core business. It's not just a math expert that works in a closed environment and just focuses on numbers. He or she must be able to do all these things. But to be really effective, a data scientist must know the business, must know the domain. And to some extent, he or she ideally has a bit an awareness of the real company business comparable to the awareness of the business and the domain we expect, to use a Scrum term, from a product owner. At the same time, knowledge and mastery of abstract mathematics is great, is a due thing. Abstract mathematics is and remains a powerful tool, but without a clear business focus, a data scientist can hardly give substance to the company that pays him or her. So let's say you have a team of data science in your organization. What is given a task? What is the typical outcome you can expect? I would say a runnable model, so something that is a proof of concept that, given certain data in a certain format, something business interesting can be generated. We are not talking about most of the time, we're not talking about production ready products. We are most of the time talking about prototypes, proofs of concepts. Okay, with data in this form and assuming that data is always in this form and delivering this value, we can produce this with a percentage of error particularly low. But we are far from taking the outcome of data science, the typical outcome of a data science team, and put that as is into production. Forget it. So why then so many companies are just pushing out job posts looking for data scientists? Why is the profession of a data scientist considered one of the sexiest jobs of these days? There's a lot of hype. But again, the hype that is obviously there, visible to everyone, is not a way to dismiss the relevance, the importance of being a data scientist. So the point is not that data scientists are not particularly valuable professions. The point is that only a data scientist won't let you as a company achieve necessarily business goals. That's the point. You need also other roles. Now, a pure data science theme that operates in a way disconnected or not particularly connected to the core business of the company is an investment that makes plenty of sense for a large organization that produces, because of its nature, very large quantities of data. I'm thinking about an energy utility. I'm thinking about a financial institution, a media company, any company active in sports. I mean, I think it's news a few days ago that a popular football team, Manchester City, the management of this company that controls up to 10 different teams in various countries and various levels, is building up an AI team, as they call it, an AI wonder team, dream team, to capture as much info as possible, to store as much info as possible, and make elaboration on that with the purpose of improving as much as possible the performance of the various players and the various teams. So in these scenarios, investment, even multi-million investments, to create a team of data science and just let them think, giving a loose direction. Okay, we would like ideally to get there. Give us suggestions of how to do it or how to get there. That makes full sense. But if you are a large and, let's say, rich organization, what if you are instead a small company with a significantly more limited budget? Now, as I see things, for what is worth my experience in the area, I would say that before a data scientist, you need data engineers. And the outcome of some applied data science is, in this particular case, much cheaper if bought as a service. Does anybody need then a team of data scientists? Again, I have nothing against, nothing personal against data scientists, but I'm just trying to call attention on the fact that it's not just data science, pure data science. Data science, something that we can compare to modern data science is a concept that in history we have seen many times, and we have studied on history books. Kingdoms of the past centuries used to support expeditions in unknown territories, whether Africa, whether the America, whether Far East, whether Australia, the area of the world where now we know there is Australia, with the hope of getting something that could be turned into a financial return. The most illustrious example of this is the discovery of America by Columbus, but also Magellan got enough money to organize an expedition to try to reach out to the other part of the world, going eastward instead of westward. That was the point, because going to India, that was the goal. But going to India westward, the known path to it, was kind of generating troubles, and it was so crucial that the Kingdom of Spain found acceptable taking the risk of financing an expedition that, according to the known geography, to suppositions, to hunches of the time, could say, well, we could try to reach out India traveling eastward instead of westward. That was a bet done in the hope of getting a significant financial return. And it was the science of the time that put in the mind of the kings the idea that maybe this is doable. They probably brought on the table some evidence or some just hunches, concrete hunches, that traveling eastward was possible. And actually, okay, they obtained some sort of a result. Okay, now science, astronomy, geography just provided evidence that traveling eastward could possibly, eventually, bring people to reach India. But then it was a matter of having sailors, having ships, having captains to physically go on a ship, take the sea, and just navigate. In terms of data machine learning, this is data engineers. So let's talk about the role of data engineers. A data engineer is exposed to data, and it's also exposed to the transformation of the data done by a trained model, but is primarily responsible for deciding how is data stored and on a daily, hourly, weekly basis, how to automate the copy and the transformation of data from the original format as it comes generated by the business running into some effective intermediate format. I mentioned earlier the concept of a data lake. Now, generally, the data lake is a place where you just dump data in whatever format, whether office files, whether text files, whether email files, whether binary files, image files, whatever. It's just dumped there in this in a fluid way, fluid as water, the data lake, and then to take advantage of this data, that data needs to be inevitably transformed into something more structured. And you need to move from the concept of a data lake to the concept of a data warehouse, in which data is organized in some sort of regular, rigorous way. And doing the shift is one of the responsibilities of the data engineer. So and the engineer is responsible for deciding what kind of transformation is required for the data to be useful and for a model to be devised and put into action, and how to automate this so that it can be made run all the time. And what is the performance of the infrastructure, the ML ops, just to use a popular term, and how is the performance of the computation graph once put into production? How close are the data that comes from the real world to the data the model was trained on? How often is the model expected to need to be retrained to stay adherent to live data? Just to make it clear, a trained model, whether a neural network or just plain shallow learning algorithm, when it goes into production, is like you having got your driving license the first time. You go to school, to the driving school, you do your tests, you do your driving tests, you pass the exam, the final exam, you got your driving license. The first moment you get yourself alone into the car in production, the first time, all you know is what you have learned, what you have been trained on, which is awfully close to the real life experiences you can have while driving, but not necessarily. As a human driving your car, the more you drive, the more you learn. But it's not necessarily true for models. A model in production, unless you retrain and redeploy it regularly, is as expert as you the first time driving after passing your exam. This is a responsibility that the data engineer has, and it puts inevitably the data engineer role in a tight relationship to the role of the data scientist. If retraining proves to be a frequent operation, then it should be found a way to automate any related tasks, just collecting updated data sets, running of the training, deployment of the up-to-date model. Again, this is what goes under the umbrella term of MLOps. You can hardly expect all these skills from the same figure that you expect to be proficient in math, in stats, and in the theory of neural network and the frameworks, mostly Python-based, used to build neural networks. Then data manipulation. Now, when you put yourself in the shoes of a data scientist, you focus on a sort of a static snapshot of data to probe that an idea makes sense. So you mostly work on sparse files that are so easy and so effective to be manipulated via, say, Python. You probe your idea, you provide evidence that some results, some information can be safely and realistically extracted from the data. But that is a proof of a concept. Then, to make that into a production application, there is the need for having a robust infrastructure, which means that probably from sparse CSV or TSV files, you have to move to some sort of database, whether relational, SQL, graph, and then you need to be proficient with query languages, not just Python. And maybe next up, you need to move into more classic programming, software programming. In one hand, we need to build that. We expect to have a figure in the organization that is perfectly able to organize AETL pipelines, extract, transform, load pipelines. Data science, by its nature, is tempted to focus on just a static sample of data, which is representative of the business domain. But then companies need applications that drive dynamic live data through the model and an infrastructure scalable enough to support real workloads. Now, an extract, a transform, load pipeline, how do you call it? It's software. So, applying data science role is not enough. Not that it doesn't matter. It's not enough. And it's not enough because it won't solve alone any practical, real problem. Now, I mentioned many times so far, role of data scientist, role of data engineer. We'll talk about role of ML developer. A role is not an individual, doesn't refer to a physical person. Role is simply the set of skills that an individual is expected to have, the actions she's expected to take in a given business context. A professional is an individual that has personally enough skill to cover one or more roles. So when I say the role of data scientist, the role of data engineer, doesn't mean that I'm suggesting that every company hires 10 different people. But I'm just suggesting that companies think that they need to have professional figures that can cover at least the 3 different roles of data scientist, data engineering, and software developer with some expertise in ML. The same individual may be able to cover multiple roles at least, if not from day one, at least, over time through education. Now let's talk about ML engineers. Here, the role of the ML engineer refers primarily to a software developer, plain software developer with some specific skills in machine learning. Which kind of skills and how deep? I would say skills sufficient to support a basic interaction with the team that does data science and that does data engineering. Of course, it goes without saying that a data engineer can be a software developer. And if the software developer as an individual is particularly willing to learn, can even develop some data science skills. So again, the point is not how many individuals you should have, but which roles you should have covered to some extent in your organization to be able to arrange effective and concrete solutions that make your products more intelligent. From an ML engineer, I personally would expect familiarity with machine learning frameworks, for example, Python-based frameworks, and more than that, the activities that make up the typical ML pipeline. So finding data, organizing data, transforming data, loading and processing data, major characteristics of the classes of algorithms and their relevance to the specific problem, typical problems that you can approach with ML, basic knowledge of the theory of neural networks, and then, in addition to all of this, of course, strong programming skills. So the ability to write good code using applying best practices from object orientation to dependency injection to unit testing, solid principles, patterns, whatever that contributes to make you a good software developer and comfortable with APIs, endpoints, web services, REST, and gRPC, or whatever, TCP, whatever kind of network protocol can help you out connecting and calling external endpoints. So, as I say things, at the moment I perceive the space of machine learning too much oriented towards a T-shaped kind of knowledge. Now, T-shaped, think just of the shape of the T letter, maybe rotated. Actually flipped horizontally. T-shape means being deep vertical, the leg of the T in one particular area, while holding a basic, very basic knowledge in a number of other side areas. So you're great at one thing, but you know enough about a number of other topics. This is, okay, I'm a data scientist or I'm a developer and I have an idea of what is machine learning. I'm a data scientist, I know everything about math, about stats, about neural networks, but I know that, well, at some point you need to write some code and Python is more than enough. I tend to contrast this vision and introduce instead, in alternative, another type of knowledge, Y-shaped knowledge. Now, compare the shape of the T versus the shape of the Y. And again, flip horizontally the Y to have an idea. So in that case, you find, yes, okay, a leg that reaches the same height as the T. So you're deep vertically in one area, but you're not having just a basic knowledge in a number of other side areas, but you're having a good enough knowledge in a smaller number of side areas. So you're not just a data scientist or the data engineer or the software expert, but you are a software expert that knows about ML. You are a data engineer that knows about software. You may be a data engineer that knows about data science. This helps, blurring the regions of business in which individuals in a company operate, and helps, getting the best along the arrow that goes from raw data to final production applications. Now, the core responsibility of the ML engineer, ML software developer role is that of physically incorporating an externally trained model into a client application. In the vision of a shaped knowledge, we can also expect sometimes from ML engineers some skills on the more delicate task of supervising the building and the training of a model based on data science specs. It's probably unrealistic, but not completely out of place, to expect business and math guidance from an ML engineer. But it's not as much unrealistic as it could be to hire a data scientist and believe you're done. You need multiple figures. One individual, whether data scientist or whether developer with whether data scientist with software skills or a software expert with data science skill, a single individual, a single role would hardly be able to give you what you need to go successfully to production. And now, let me talk about a specific library called ML.NET, part of .NET 5 and part of .NET 6 and part of the Microsoft .NET framework for the years to come. Now, when I started working on this product and having several conversations with the development team already 2.5 years ago. And I confess that my original approach to this was, oh, okay, cool, so cool. It's the .NET version of Python libraries, specifically scikit, the scikit library from Python, which is the most popular shallow learning library. And I was kind of disappointed when I figured out that ML.NET was not able to let you create neural networks. I was just dreaming of seeing myself getting rid of TensorFlow, Keras, PyTorch, and do everything in my lovely C# environment, Visual Studio environment. But then I got feedback from the team that in a way deeply impacted my perspective of what it means doing ML, machine learning in the real world. ML.NET is not the framework for data science. It has little, not nothing, but little to do with being simply the .NET counterpart of scikit-learn Python framework. It has nothing to do with Keras, with TensorFlow, with PyTorch. But at the same time, ML.NET excels at letting you creating in your favorite .NET environment using a top quality language like C#, data loading pipelines, data processing pipelines, to arrange through Azure services in case, training and testing pipelines, and to make it snap to take a model and integrate, encapsulate in a client infrastructure. ML.NET gives you a class that wraps up a trained model, which in the end is a serialized file, binary file, and it gives you a class that is so easy to call from an ASP.NET MVC application. So in the end, integrating means just calling an in-process class, which makes performance hugely better than calling a web service, than calling an external web service, because it removes at the very, very minimum the network latency, but there is more than that. So ML.NET is a tool for data engineers and for ML developers. It's not primarily a tool for data scientists, But it could be a tool also for practicing as far as shallow learning is concerned. People, .NET people, to slightly move towards data science. But if I have, as a data scientist, a strong Python-based skills, or if I'm a neural network expert, ML.NET is not the tool for me, but to make the product of my work, so my Keras-based neural network, saved as in an Onyx format, I can import that in ML.NET and consume it natively in process from my ASP.NET application. This is really cool. So, to cut a long story short, approaching the end of the presentation, as I told in the beginning, science in history and also in artificial intelligence, science proves that something is possible, but engineering predictionizes it. This is in history, has always been like this in history. Think of, I don't know, my hero in science, Michael Faraday, the immense person who discovered the relationship between magnetism and electricity in the late 19th century. In the Victorian London of the time, he was of humble origins, and he reached the heights of the Royal Science Society. It was the guy who proved that induction, what we call today induction, and we cook our food on in modern kitchens, that was possible. But it's the guy of the Faraday's cage that, you know, for decades we have found in airplanes and cars to protect ourselves from lightning. It built nothing like that, but it built that something was possible. Think of Kurt Gödel, the master of logic. He in some way proved that calculation was possible, and then he came Alan Turing, which was a scientist, a math person, but also with some engineering skills. Or think of John von Neumann. I mean, science proves that something is possible, but it's engineering that productionizes it. And okay, and in history we have seen many examples of people who are scientists, but also good engineers. It's exactly the same when we think of AI. Data science proves that achieving something with the available data is possible, but then it's data engineering and in the end software that turns that into products that can be sold and can make money, can bring money back. In history and in AI, nothing is really different. AI is no magic, but far from being BS. Okay, I think that I'm pretty much on time. So if there are any questions, I'm here to answer. Otherwise, let me know what to do.
Yes, we have a question, but first, thank you very much, Dino, for your session. I think you raised quite serious questions, and maybe personally, I would like to rewatch your session one more time, just to like understand, you know, all the hidden treasures of your statements. And thank you very much. And the question is quite concrete. Maxim is asking, in your opinion, from which field is it easier to become a data engineer? From data scientist or from machine learning engineer? So what's your personal take on this?
It's not an easy question. Let me mention an anecdote as a starting point towards making a statement that answers finally the question. Was maybe some couple of years ago. I was visiting a huge customer, an energy utility, and as I was in the hall trying to make authorization badges and pass to get into the building. So next to me and the group of people I was part of, we saw a swarm of people, having giving the vague idea of being hippies with long hairs, blonde hairs. I mean, yeah, completely different. They were in contrast with the typical aspect of any other people in the same building, getting into the same building. And it was inevitable to have a look at these guys. And one of my people in my group said, "Oh, that's the company data science team." So I got to learn that this company, huge energy utility, they hired a bunch of probably 20 people, uh, give them space, money, funds, resources to just think, and of course access to data, to just think and see what kind of product, what kind of outcomes they could produce using the math, the stats, and of course the native energy data. So in this scenario, that was a team completely disconnected from the real products, consumer products that this company was selling. Now, this is not a pattern that I expect so easy to be in just any company, especially if you are not such a large company. So for a normal business scenario, you need to, okay, you have some data, but you need to find the effective way to turn that data into a product. You need someone that has the idea of what you can do. The idea is mostly a matter of marketing. The business idea is always related to marketing. Once the idea comes out, it's a matter of finding, okay, a data science solution. Okay, what do we need a neural network? Which kind of algorithms we can try? What kind of data we need to have? And then organizing the things. So this, for the most part, is the job of data scientists. But then going towards production, other roles come out. So I would say to get closer to the final answer, I think that in general it could be both ways. You can start as a developer, you can start learning more and more and more about machine learning, or you can have a strong mathematical skills, and then you can move towards software. So if you're a developer practicing with, say, ML.NET, much more than practicing with Python libraries, makes you aware of the issues, the challenges, the pipelines that are part of any ML practical solution. At the same time, if you are coming from a math background and you are curious about software, because you must be curious about software, then Python is the starting way that allows you to practice with things, but then you can still go on and learning more and more about software, but first you go through data engineering, because you cannot be overnight from math skills to be a great developer and vice versa. So data engineering is something in the middle that requires data manipulation skills, but you can get there technically from both sides.